Hi and welcome to GeeksforGeeks. I'm Siddharth Hazra and today we would be discussing the problem number of good components. If you understand the definition of this problem and you don't try to complicate your mind then and hit your mind like crash your mind with simpler ideas, this question is on the simpler side. So in this problem you're told to find the number of good components. And what is the definition of number of good component? The definition of number of good component is that each node should have a path to all of its nodes. Didn't understand to that extent? Don't worry. What I meant is that we don't have any via thing. I am trying to build out a road network where I don't want any via thing between any of. This just means that let's say we have one, we have two, and we have three. Okay, and the path is this. So now see, if we have three houses and there is a path like this makes sense. And this is a component, but you have a problem here. That from 2, I don't need to go surpassing any node and I can directly visit all the other nodes in this component. But I can't do the same thing for 3. Like from 3, I can visit the node 2 without any encountering any node in between. But if I want to visit 1, then I need to encounter 2, I need to visit 2 and then visit this. So this just means that no node should have any via thing. Like every node should have a direct edge to all the other nodes in that component. So if I analyze this example, if I see up this, it just means that if there are 3 nodes in this component, then 3 should have a direct edge. Like if no edge is repeated, like no edge can be repeated. So if each edge is pointing towards a unique node, then if the number of components are 3, then 3 should have a direct edge to all other means what? If there were 3 elements, if there are 3 elements, then this value should have a direct connection to this person and this person, that is 2. So I can say that it requires 2. Same goes for this, same goes for this. And we know that in a graph there is no duplicate edge. Like we don't have anything, we don't have a condition like this. Like we don't have 2 edges to the same node. We don't have this condition. So we can say that each node in a component, to become a good component, the condition are that each node should have n minus 1 edges, because no edge would be repeated. If everyone has n minus 1 edges inside a component, then it is a good component. I can claim this. And you can do this by just, and you can see this is true if we just remove up this side. The remaining values would be good enough. So if we take out the second example and we have here 1, we have here 2, and if we have here as 7, then here we have 3, and here we have 4, and here we have 5, and here we have something like 6. If I draw out the edge, it would be like this. Now we need to find the number of good components. So what we can do is, see this idea. Like we started DFS from 7. By doing a DFS over 7, we had a visit to 7, 2, and 1. So we would just simply keep it 7, 2, and 1. And we would just count how many nodes I had, like how many nodes I visit when I did a DFS. Just I would say that, because the count is important, as we saw. The count is 3. And how many nodes I visit? 7 to 1. So I would now go and check if the 7 has n minus 1 edges on it. I would say no, 7 does not have n minus 1 edges. So there is a false condition. So we can just simply break out from this point and we can say that yes, this is not a good component. So I would say this is not a good component. That too. Now I would do the same thing. So every time I would just keep a track of, I would start a DFS, keep a track of how many nodes I'm visiting and the count of nodes I'm visiting. And that's enough, because the size in the adjacency list would give me the number of edges. So now again, if I see up this, if I start a DFS from 6, I would visit 6 and the number of nodes I have visited is 1. So now I would simply go and check if 6 has 0 edges or not. And yes, 6 has 0 edges. So no violation of rules. So this goes up true. So we found one good node. If I talk about the very last one, so if I do a DFS over 3, we would do a DFS of 3, 4, and 5. How many nodes we did visit? We had to visit 3 nodes. So now we would go and check if the number of edges in 3 is 2 or not. Yes, it is 2. If the number of edges in 4 is number of nodes minus 1 or not. Yes, 2. If the number of edges in 5 is 3 minus 1 or not. Yes, it is indeed. So no violation of rules. This comes under the category of good node. So out of 3 components, 2 were good components. So we had a count of 2. So what do we really need to do is that this is the code of DFS. This is the very simple code of DFS. That is, we have a DFS function. We have a source. And then we mark the source as visited. And then we iterate over all its neighbors. Auto I am writing, like auto is nothing but like Python, like it would be automatically assigned what is inside there. So I write auto a lot. So in Java you need to specify. So I would just write auto to be very specific, or I can just do something like we would visit all the neighbors of G of S by using a for each loop, and we would again say that if this neighbor is not visited, if this neighbor is not visited, do a DFS of this neighbor too. This is the code of DFS. What changes do I need? The changes that is required is count of the number of nodes that is done through DFS and all the nodes that I am visiting. Okay, and list of nodes. So list of nodes. So see, if we want to count and list out all the nodes, so every node would come as a parameter here. So here only I can just add up this, that count is equal to plus plus, because every node would come inside this DFS function exactly once, and the list of the nodes also. So list of the nodes is just nothing, like we would just keep it inside a data structure. So any data structure, just dot add, I'm writing it for simplicity so everyone can understand, just add this new value, that is S. Now see how this would work. Now let us see how this would work. Now this is very important. The dry run is extremely important. So now if I have the value as 1, the value as 2, and the value as 3. Now what we would do is, we started a DFS from S, we marked it visited, and then we inserted one S into that data structure DS, and the count which was initially passed as 0 is incremented by 1. Then this one told me that I have one neighbor which is not visited. So I went up to this and called the DFS function for 2. This got added into this data structure and the count was incremented, and then this 2 told me that I have also a neighbor which is unvisited, that is 3, because 1 is already visited. So now I would call the DFS for 3. So 3 would get inside the data structure, the count would increase, and this is how I get the list of all the nodes and the count inside this component. Now I can just check for each node if you have the number of edges as count minus 1 or not. Pretty simple. Now there is one more formula, that each node, like, or the sum of all the nodes should be equal to n multiplied by n minus 1. Okay, if you are an intermediate person, you can think in this fashion. Total number of nodes would be using this formula of n multiplied by n minus 1, so you can just count the number of edges for everyone. But if I just move forward with intuition, if I move forward with, like, you I'm thinking that it should be very easy to move forward to the solution. If I move forward with intuition, this is the easiest solution I can get. So the dry run of DFS function is done. Now let us see the main function. So now, as we do in the DFS, I initialized a vector of size v plus 1 because the nodes are 1 indexed, and marked everything as 0, initialized everything as 0, that no one is visited up till now. Then we start iterating from first node to all the nodes. If we find a non-visited node, then we start a DFS from him and give him a data structure where he can give me all the list of nodes. We initialize it each time because the list would be different, and we don't want any pre-existing elements of any other DFS to interfere with this. That is why we declare this locally inside before each DFS is called. Then we say that we don't have any false condition, like no rule has been broken for good. Like initially we say that this, like what we do, like when I'm a teacher and I go inside the class, I assume that the class is made up of good students. And now as we move further, as I start teaching, I get to know which all people are serious, which all people are not serious. In terms of you, where you would relate is that initially when you go to a college or you get admitted in a college, initially in the very first year of your college, everyone seems a friend of yours. As you gradually start spending time, you find some of the condition which don't match with your criteria of friends, and then you say that yes, my circle is not right, and then you need to move out of that circle. And this is the idea of using a flag. Initially we say that we have a good circle and this is a good component, and if at any point we find that a condition is broken, I say that my circle is not good, I need to change my circle. Here we say that this component is not good, because every node should respect the criteria of a good component. So then, if it remains true, if the friendship of the very first year remains till the end, we say it's a successful friendship. Same goes for this. If no rule is broken, even at the end, we just take it as a good component. Okay. In the same manner, what we start doing is we this temp would now after we call the DFS, this temp function would have all the nodes that are visited by this DFS. Then we start iterating over all the nodes, and then we see that if any of the nodes has the number of edges less than what is needed, we say a void condition is made, and we break from there. At the end, whatever is the scenario, we increment that. So now let us see if the solution works or not. So this is the solution. Let us compile and then see how many errors are we making. We see that no errors are being made. Now let us try to submit this and see if we can get an AC or not. And this you got an AC. That's it for today. But if you want this hard work and this energy and this teaching should be justified, then comment at least a 1 in the comment section so that the reach of this video could be increased and this work could be justified. That's it for today. Thank you and have a nice day.